In this video, we're going to be working further with the calculus on polar curves. In the previous lesson, we talked about dr d theta, and that was sort of one of our first experiences with working with derivatives on polar curves. And now we're going to be looking at different derivatives. Instead of dr d theta, we'll be looking at some other things. And something that I want you to recall is that if you have a polar curve, like some function of theta, we can find expressions for the x and y coordinates of the points. So keep in mind, usually polar is done with r and theta, but we can convert those to x and y by using these formula. Right? We have x equal to r cosine theta and y being equal to r sine theta, where r is whatever your function of theta is. So as long as you remember that we can get our x and y coordinates by doing that, we can effectively look at the rate of change of x and the rate of change of y. And so like we just said, we can find the rates of change of the x and y coordinates by finding dx d theta and dy d theta. All it's going to mean is that before we go about finding these derivatives, we figure out first what x is. We compute r cosine theta, and we figure out what y is. We compute it as r sine theta. And then from there, because remember that r is a function of theta, both of these are going to be functions of theta, once we have these expressions, we can find dx d theta and dy d theta, and effectively find out the rate of change of x and the rate of change of y. So I have one example that we'll look at. Suppose that we have the polar curve r equals 1 minus 3 sine theta, and we'll look at a graph of that later. For part A, I just want us to find expressions for the x and y coordinates of the points on the curve. So go ahead and pause the video, do part A, and then re-watch and check and make sure that you've got that right. So for part A, when we want to find the x and y coordinates, our x coordinate will simply be our function, 1 minus 3 sine theta times cosine theta, and my y coordinate will be 1 minus 3 sine theta times sine theta, right? Both of these things are simply r times cosine theta or r times the sine of theta. So that's part A, yay. Part B, we now want to find expressions for dx d theta and dy d theta. In other words, I want to take the derivatives of my x expression and of my y expression. And you have a choice here. You can either multiply this out and then take the derivative, or you can simply take the derivative and sort of use the product rule as we're going along. And I can't even make up my mind. I think I will distribute through first. So that means I'm going to rewrite this as x equals cosine theta minus 3 sine theta cosine theta. And then when I take this derivative, dx d theta will be negative sine theta. And then this thing here is going to require the product rule. So this will be minus 3 cosine squared theta. And then we'll leave this part alone and do the derivative of cosine, which would be negative sine. So plus 3 sine squared theta. So this is my expression for dx d theta. By the way, this right here is really tempting to simplify. We feel like we see cosine squared theta plus sine squared theta, but remember one of them is negative. We can't just change this into 1. Okay? So that's my dx d theta. Now I can move on and do dy d theta. Same thing, I'll begin by distributing that through. This will give me sine theta minus 3 sine theta cosine theta. I'm sorry, that's 3 sine squared theta this time. 3 sine squared theta, there we go. So now our dy d theta will be cosine theta minus 6 sine theta times the derivative of sine theta will be cosine theta. And so here's my dy d theta. Keep in mind that right here we could factor a cosine out of this thing, and that could be valuable. If we were ever asked to find out where dy d theta was 0, which we may be at some point, we would want to find out where that thing is equal to 0, and factoring would help us a lot with that. So just keep that in mind. Now part C asks us to compute the values of dx d theta and dy d theta when theta is pi over 4. So we're going to want to take pi over 4, input that value here, and find out what dx d theta and dy d theta are. We're then going to want to use those things to determine the direction the particle is moving. So we're going to take a look at that next. So if you haven't already done so, pause the video and evaluate these things for pi over 4. So first I'll do dx d theta. So for part C, dx d theta. So if I'm inputting pi over 4 here, That means I'm going to get negative square root of 2 over 2 minus 3 times, that'll be the square root of 2 over 2 squared, plus 3 times the square root of 2 over 2 squared. We can simplify this further. dx d theta will be negative root 2 over 2 minus 3 halves plus 3 halves. So we end up finding that dx d theta will simply be negative root 2 over 2. So there's my dx d theta. We now do the same thing for dy d theta. dy d theta will be square root of 2 over 2 minus 6 times root 2 over 2, and there's going to be 2 of those effectively. So if I continue simplifying this, dy d theta will be root 2 over 2 minus 6 times 1/2. So that's root 2 over 2 minus 3. And what's important about both of these is that this is clearly negative, and this is also pretty clearly negative. Right? I mean, the square root of 2 over 2 is less than 1, so when you subtract 3 from that, it's still going to be negative. The question asked us to determine the direction the particle was moving. Because dx d theta is negative, it means that as theta increases, if theta is changing positively, which it is, if theta is changing, then x is changing in a negative direction. Same thing down here. If theta is changing positively, then y is changing negatively. So what this means is it means that x and y are both moving in the negative direction. So we expect that at this point, our point is moving left and downward. So what I'd like to do now is I'd like to graph this function, show you this polar curve, and show you that at that value, the particle should be moving left and down. All right, so here's the graph. Here's the graph of 1 minus 3 sine theta, right? And we were asked to look at the point where theta was pi over 4. So pi over 4 is a 45-degree angle. So what I'm going to do is I'm going to sort of just imagine, like if I was looking at a 45-degree angle, I would basically be looking at the line y equals 1. I'm sorry, y equals x, right? So I was trying to sort of go through that point right there. So our value for pi over 4 must be right there. My graph must have started over here with theta being 0, and these are sort of the small angular values. This right here is pi over 4. I hope you guys understand why that's pi over 4. And you'll notice that as the particle is going that direction, right when I get to that point, I am moving left and down, right? I'm moving in a negative x direction and a negative y direction. The graph confirms the answer that I got, that dx d theta and dy d theta are both negative.